So let's start. We have here Tan Tui. She received her undergraduate degree in physics and astronomy from Penn State University. Then she did a master's degree in Cambridge, and then a PhD. She got a PhD in astrophysics from the Chinese Academy of Science in 2020. She was then a postdoc fellow in DAMP in Cambridge, and she's now a postdoc in CITA in Toronto. So her research interest lies in protoplanetary disks with emphasis on analytical and computational methods. Thanks, Sam.
Thanks for the introduction, and thanks for having me here. Do I have a pointer? No? Okay, that's fine. So I guess I'll talk about the gas dynamics in protoplanetary disk and the disk today. My collaborators have been working with Henrik, Gordon, Seba, Quinton, Minka, and Xueling for various projects, and Teresa, Yishan, and Eleanor, they are my summer interns. Teresa is from UCL, Yishan is from Oxford, and Eleanor is now an Oxford PhD student in maths. So just a quick introduction on the planetary systems. So the planetary systems start out from a molecular cloud. Then the cloud is gravitationally unstable and it will collapse under its own gravity. Then the majority of the material will end up with forming a protostatic center, and the remaining material will be forming a protoplanetary disk around the protostar. The protoplanetary disks will dissipate over 1 to 10 million years, and then the planetary system will evolve into a more mature state where we have a planetesimal belt orbiting around the main sequence star. That's a debris disk. The closest debris disk systems, our solar system, we have the Kuiper belt and the asteroid belt. They are the main components of the debris disk in the solar system. Just to compare briefly the protoplanetary disks and debris disks. They are protoplanetary disks orbiting around the pre-main sequence star. They are the birthplace of planets, and we have gas and dust in the disk. They usually dissipate over 1 to 10 million years. And then the planetary system will evolve. We will have a planetesimal belt. I'll try to use this one. Okay. So the planetary system will evolve into a debris disk. So the debris disk is orbiting around the main sequence star. That's the planetesimals are the remnants of planet formation. Those planetesimals are growing up from the little dust in the protoplanetary disk stage. The main composition for the debris disk, we have planetesimals and little dust derived from them, and we also have little gas in the debris disk. The age they can survive for gigayears. Okay, so let's start from the gas dynamics in protoplanetary disks. So to understand the gas dynamics, we need a little introduction on the ionization fraction in the disk. And the ionization fraction, we have two components. We have thermal ionization and non-thermal ionization. The thermal ionization depends on the temperature in the disk, which is primarily passively set by the central star. So if we go to the very inner region, say less than 0.1 AU, then the temperature is high, it's reaching 1000 Kelvin, and the gas is fully ionized. It is coupled with the magnetic fields very well. So we're in the ideal MHD regime where the gas is coupled with the magnetic fields. But if we go to the outer regions, the larger than 0.1 AU, then the temperature is low, so the thermal ionization is weak. The gas is not fully ionized, and it's it's not in the ideal MHD regime, and we need some non-ideal MHD effect to describe the gas dynamics. And there are in total, we have 3 non-ideal MHD effects. We have the omega resistivity, we have Hall effect, and Hall diffusion. So in the same ionization fraction, the ample diffusion is dominated at the strong magnetic field at low densities. The omega resistivity dominates at weak magnetic field and strong densities, and the Hall effect is in between them. So in a realistic disk, we have ample diffusion dominates at the outer region of the disk and near the surface of the disk because of the low densities. And the omega resistivity is at the midpoint and inner region of the disk because of the high densities, and we have the Hall effect in between them. So in this talk, I'm going to focus on the outer region of the disk from 30 AU to 100 AU. So the ample diffusion is the dominant non-MHD effect. It is known that the mass equation or the angular momentum transport in proton potential disks are dominated by the magnetized disk wings, but it is a bit problematic because this mechanism of magnetized wind will lead to a laminar disk, but from observations from the non-thermal broadening of molecular line emissions, we see that we do need some turbulence, weak turbulence in the disk, and the turbulence level is on the 0.01 to 0.1 of the local sound speed. So so in this talk, I'm going to discuss two instabilities that can drive weak turbulence in proton disks. I'll discuss about the magnetorotation instability, and I will talk about the vertical shear instability. So in this scenario, we'll have magnetized wings at an atmosphere, and in the disk, we can have either VSI or MI, or maybe they can coexist. So to understand the MI turbulence, I conducted 3D simulations. It's not the MHD simulation applicable to the outer region of the disk. So we have ample diffusion incorporated in the simulation, and it is done by CNet++. The simulation domain is dimensionless, so the radial domain starts from 1 to 100, theta domain from 0 to pi, and the azimuth domain from pi 0 to pi over 4. So we're simulating an edge, it's not like an entire sphere. We use static mesh refinement to achieve 32 cells per H in R and theta, and 16 cells per H in azimuth. 3 parameters in the simulation. We have ampola diffusion Alsace number, which quantifies the ampola diffusion strength. And this AM, the Alsace number, is inverse proportional to the diffusivity eta here. Another parameter is the magnetization in the disk, which is parameterized by the plasma beta. It is defined as the ratio of the gas pressure to the magnetic pressure. And the last parameter is the cooling time scale in the disk, and we set to the local optical time scale for the MRI simulations. So I'm going to show yeah.
So what makes the choice of the grid refinement this way? How do you choose to refine the grid this way and not another way?
You mean like?
Yes, like why?
Okay.
Like why the refinement at its place? And,
yeah. So.
Why this choice of refinement? So, yeah.
Yeah. So we have like more finer grids at the midplane because we want to resolve the instability in the disk.
Yes, but why do you stop there in a sense, like to be super refined and not like why not refining like higher up or like is there is this choice of refinement affecting the simulation or?
Yeah, so this simulation, if you don't do static mesh refinement, it's going to take, I don't know, but using static mesh refinement is already it will take you 2 to 3 weeks to run for one simulation. So that's fine.
Yeah, so you save some time, but in terms of quality of the simulation, so how do you control the fact that your results do not depend on the choice of refinement you make?
Yeah, I guess it's fine because if you want to study the MI, it's in the disk rather than in the atmosphere, right? So you want more resolution in the midplane rather than in the other place. Yeah. So this is going to be a movie for the fiducial simulation. Left panel is the radio velocity. Middle panel is the Meridian magnetic field. You can take it as the vertical magnetic field at the midplane. And on the right-hand side, you have the azimuth magnetic field. If you look at the left panel, we see the MI turbulence going on as time evolves. And the middle panel, we see something interesting because the vertical magnetic field, I'm going to play the movie for another time. So in the middle panel, you find the vertical magnetic fields, they are concentrated into magnetic flux at multiple radio locations, right? So this phenomenon is interesting, and I'm going to detail that in the next few slides. So the main conclusion from this simulation is that we do find the magnetized disk wings can coexist with the MI. So we have the MHD wings dominate for the angular momentum transport, and we have the MI turbulence, MI drives weak turbulence, and the turbulence strength is comparable to the observational measure values. And in this plot, we see the MIs in the disk region, and we have MHD wings in the atmosphere.
Okay, to the lines, so you are drawing two lines there. To the lines, like, yeah, and to the lines, they correspond to the place where it is refined?
Roughly. So these two lines corresponds to, I would say, somewhere in between here.
It's a jump of gradient.
It's a jump of temperature of M-polar diffusion strength. It's more like the it differentiates. It's like you have the X gradient in between the lines, and you have the atmosphere afterwards.
So the question is there a way to know whether the fact that this MRI region is confined here is due to like this physical condition, or is it a numerical artifact, or it's a combination of the two things?
Yeah, so I would say this is physical because I don't think you have MI there because you have the MHD wind launching instead. Okay, so this is the plot for the magnetic flux concentration I just showed. The radio domain, the x-axis is the radio locations in the simulation, and the y-axis is the simulation time in the innermost orbital time scale, and the colors for the vertical magnetic fields. So different panels are for different M-polar diffusion sensor numbers for different M-polar diffusion strengths. If you look at the first four panels, you see the vertical magnetic fields, they are all concentrated into flux sheets at different locations, right? Some of them are like propagating radially outwards, and some of them are quite static. But if you have really strong MI turbulence, then the turbulence will disrupt the magnetic flux concentration phenomenon. So why this is interesting? Because they are non-uniform distribution of magnetic fields in radius. Listed the radio pressure variations or the radio gas surface density variations. Those panels, again, the axis is the radio locations, the y-axis is the gas surface density. Different plots are for different M-polar diffusion strands and also for different initial magnetic field strands. The colors, the light colors are for the earlier simulation time, the dark colors for the later simulation time. So you see these panels, they are radio surface density variation develop over time, and also the pressure because they are linked by the sound speed. And this radio pressure variations could lead to the iridescent gaps that are frequently observed by the ALMA. So the most popular explanation for these rings in the gaps are, of course, the planets, they can carve gaps in the disk, but we find the magnetic flux concentration, they can also generate this rings in the gaps. And this phenomenon, this mechanism is particularly appealing to early class 0, class 1 disks, where the massive planets are not formed yet. So right-hand side is a synthesized image, not from my simulation, but from Rios and the Swift simulation. Those rings and the gaps seen in their synthesized image is due to the magnetic flux concentration I just talked about. Okay, so this is a 3D simulation. We'll also look at the azimuthal features in the fiducial simulation, and we find the magnetic fields and surface density profiles. They show axisymmetry. That means we really see rings, right? And since I said there's a radial density variation in radius, it can possibly excite Rossby wave instability and lead to vortex formation, but we don't see any vortices in the simulation. That's probably because we have the very limited azimuthal domain, or it could be because of the magnetic fields. The magnetic tension force could prevent the rolling up of the vortex sheets. So that's all I want to talk about for the MI turbulence. If there are any questions.
So I remember that there was a debate whether the certification was mattering in the formation of these rings, and so is this sorted out, this debate, or it's still a question of whether?
Yeah, I think there are lots of mechanisms proposed for the rings and the gaps, but I personally, I think the planets might be there. It's a very robust mechanism to drive these rings and the gaps. But like I said, if you go to very young disks, you still see these rings and the gaps. But at that time,
we only have one case for class 0 disk rings, and EDIS has a lot of more samples. Do they have rings and gaps? I think
okay.
I really remember that they don't show any structures. I know there's one case with rings and gaps. Can you have a lot of magnetized class 0 disks without rings and gaps? According to us.
Yeah, so I think from observations, there are two systems, class 0 and class 1 disks. They have rings and gaps. Not all of them, for sure.
Right.
Yeah.
The EDIS provides a lot more samples without rings and gaps.
Okay.
So you're fine with it?
Yeah, I think I'm fine with it. It's, in early disks, you have like you have gravitational instability, you have other physics in it, right?
And how is your result different from Surana?
Oh, right. So the main difference is that they don't have enough resolution to resolve the MI turbulence in the simulation.
Right. Okay, that's really very not
On that front, if you go back to Miguel's question about the resolution as you go up on the disk, if you have an issue with requiring enough resolution at the midplane wall to get MRI turbulence, if you increase the high resolution region further up in the disk, does the transition to MRI turbulence occur further up in the disk?
Okay.
Or the MRI wind transition.
So these lines, they are not really corresponds to where the static mesh refinement. You see the transitions in the slide. It's not corresponding to those transition lines. It's because we have set ample diffusion and temperature for the initial temperature and initial ample diffusion stress. And there is a transition for the temperature and the ample diffusion stress. So I would say this line is not corresponds to where you set your mesh refinement. It's because the temperature transits here.
Is it sensitive to where you measure?
I don't know because I don't try different setting mesh refinement.
So can I ask another question? Like, what would be the easiest mechanism to quench this kind of formation of rings? Would it be self-gravity? Would it be something else dust? Would it be I don't know if there is an answer to that, but according to you, like you have a
Yes,
is it easily quenchable or not? This is my question because I've never run this kind of situation.
right. So I'm not sure if you add self-gravity, what's going to happen. But if you add dust particles, I think the dust particles will respond to the Raisson gaps rather than to remove those Raisson gaps. Yeah. It would be interesting if you add self-gravity to this kind of simulations, but no one did that yet.
Try to see if the azimuth domain can change the results.
Yeah, I didn't, but I think I didn't try like larger azimuth domain for this simulations, but I think Jifai did that, and I don't think he see the vortices in his simulation, but he said if you go to like 4-2 pi, then somehow the Raisson gas would be I'm not sure. I don't think his results are published yet, but it seems like the Raisson gaps will show different patterns than if you have like less extended azimuth domains.
No, so if people online will not hear the question, I can write a quick summary.
Okay, so that's for the MI turbulence. Now I'm going to talk something about the vertical shear instability. The vertical shear instability, or the VSI, is initially discovered back to 1960s by Goldreich in the context of differentially rotating stars. There are two conditions shall be met. Is the instability criteria. The first one is we need some vertical shear in the disk, which means the angular velocity varies over height. And that's kind of like the energy source of the instability. Another criteria is you need very fast cooling to overcome the vertical buoyancy effect. So on the right-hand side is the active zone of the VSI based on these two criteria. And you see the VSI is for the green hatches, and it spans roughly from 0.05 AU to 1 AU, and then from 10 AU to 100 AU. So that's a large part of the disk. We also have other instabilities, hydrodynamic instabilities, such as the collective overstability, and the I'm not sure what is VCI here, but it's not something I'm going to talk about. We focus on the VSI. So I'm going to show a very standard hydrodynamic simulation of the vertical shear instability. And the color is for the vertical velocity over the local sound speed. And you see that the VSI, the non-linear saturation of the VSI is dominated by this vertical coherent motions or oscillations. So the left-hand side is a one snapshot of this non-linear saturation. And by the Kolmogorov theory, we know that the large-scale turbulence eddies will cascade down eventually to very small scale, which can be dissipated by the viscosity in the disk. But the problem with the VSI is that the large-scale eddies remains over the simulation. It doesn't go to small scale and dissipate it. So we need to find a way to transfer this large scale energy to small scale. And Henrik and I proposed a way to transfer that large scale energy by wave-wave interactions. To explain what is wave-wave interaction, I'm going to show a clip of a swing oscillation system. So in this system, we actually have two waves. Or two frequencies. One frequency is actually the swing oscillation frequency. And another frequency is that this guy is pushing the scale periodically. So there's a forcing frequency from this guy. And when these two frequencies match, the amplitude will increase, right? So this is two-wave coupling, which the condition is just the first frequency of this guy equals the swing oscillation frequency. So omega 1 equals omega 2, that's simple. And then for the BSI problem, we now have three waves. And if we want to have the three waves coupled to each other, we want the omega 1 equals the add up of the second and the third frequencies. So the question is, what are these three waves or three frequencies? It turns out the VSI is overstability, so it's actually an unstable inertial wave. If you don't know what is inertial wave, it's like we have sound waves in the air. We also have other waves in accretion disks, and the inertial wave is driven by the rotation of the disk. So this VSI wave will couple with another two inertial waves in the disk. They have different frequencies and they have different wavelengths. So the VSI wave is more like this. This guy is like the energy source, because when this guy is pushing the scale, the energy transfer from this guy to the girl. So the VSI wave is like this guy. The energy from the VSI wave will eventually transfer to the other two inertial waves, and these two inertial waves gain energy, so they can be excited and becomes an instability. We did some mathematical derivations in the paper, but I'm not going to show that. Instead, I'm going to show a 2D local simulation. It's done by spectral method Snoopy, and then we use the resolution is 64 cells per wavelength in both dimensions. For simplicity, we just take the radial wavelength over the vertical wavelength of the VSI to 1. So for this Snoopy simulation, it's a local simulation. It's just a small patch.
Just a question.
Yeah.
So you choose dV0. Is it for the background? Is it for the background or for the perturbation or for both?
Which one you're talking about?
It's the dual. Okay, so everything is okay. The code is incompressible.
Yeah,
sorry. Okay.
It's there.
Sorry.
Okay.
Yeah.
Yeah.
Okay. Thank you.
Can you just repeat the question simply so people understand?
Yeah, so I guess the question is whether the simulation is incompressible or not, right? And I showed here is an incompressible simulation. It's a local simulation. Okay, so the simulation is a very small patch. In a global simulation, we just take this small patch and simulate the wave-wave interaction, or you can also call it parasitic instability, because this whole thing is based on the emergence of the VSI in the disk. So at t equals 0, that's our initial condition. that's just the VSI wave, the unstable inertial wave. And as time evolves, you can see the simulation domain is taken over actually by the two other inertial waves I just talked about. And these two other inertial waves, they have smaller wavelengths. So you can think that the energy from the large scale VSR wave cascade down to the small scale inertial waves. I haven't done the simulation myself, but this is just a local simulation telling you this parasitic instability is possible. But I think Liz and Maro done the resolution study of the VSI. They can reach like 200 cells per age in their highest run. And they find on top of the vertical coherent oscillations, there are small scale meridian vortices. This is in the RZ plane rather than in the azimuth plane. I'm not 100% sure this is due to the parametric, due to the parasitic instability, but if we go to higher resolution, we do find something quite different from the standard BSI simulations. So any question here? No questions, okay. Right, so that's what I want to talk about for the VSI saturation. Then I will just move on for the gas dynamics in debris disks. Just a quick recap. Once the proton-quench disks dissipate over 1 to 10 million years, the planetary system will evolve into a debris disk. The debris disk is composed of planetesimals around a main sequence star in a belt. So as orbiting main sequence star in the belt, we have planetesimals and dust particles derived from those planetesimals, and we also have some little gas. The age of the debris disk can survive for gigayears. So traditionally, debris disks were considered as gas poor, so we don't observe any gas for debris disks back to the old times. But recently, the gas observations have been accumulating, and now we have 30 debris disk systems with gas detected. So in a volume limited sample of bright A stars debris disk systems, we find 70 of them actually has gas.
This is beta peak, right?
This is beta peak. Yeah. So we mostly we detect molecular CO, and the CO can photodissociate very quickly into atomic carbon and oxygen by stellar and interstellar UV radiation. And this atomic carbon will be ionized and become C2. So the main composition in the debris disk gas is we have CO molecules, we have atomic carbon, oxygen, and then we also have ionized carbon. Just to compare the dust mass and the gas mass in proton-quench disks and debris disks, the dust mass, we see that for the proton-quench disks, they are much higher than debris disks. And for the CO mass, we also see lots of CO in proton-quench disks rather than in the debris disks. So the dust and gas in debris disks are tenuous. The dust to gas mass ratio for proton-quench disks usually is about 0.01, so it's less than 1. But for the debris disks, we see the dust to gas mass ratio larger than 1. So why we want to study the gas dynamics in debris disks is that the first of all, we have this lots of gas observations accumulating in the recent years. So, but for the theoretical understanding of this gas dynamics is very rare. We only have one work back to 2016 by Herrick and Quinton, and then there is no theoretical work on the gas dynamics. And another thing is that once we know the angular momentum transport, we can predict the vertical mixing and radial spreading of the gas. The vertical mixing can tell the origin of this gas, and the radial spreading, maybe this gas could contaminate the atmospheres of the nearby planets. So in our work, we just reviewed several angular momentum transport mechanisms that can drive massive accretion and turbulence. And I think the most interesting finding is that we actually find the molecular viscosity can transport a lot of angular momentum in this kind of disks, because the molecular viscosity depends on the speed of the particles. It's just the sound speed and also the mean free path, which means if the system is very tenuous, the gas is very tenuous, the mean free path here is going to be very large, and the viscosity, the molecular viscosity can be very large. So for this plot, x-axis is the scale height in the disk, y-axis is the mean free path, and different colors are for different gas densities. We see that for all of the systems, you can see the molecular viscosity can roughly reach 1 at certain heights. So to calculate this mean free path, is actually we have neutrals and we have ions in the disk. For the neutral or neutral ion collisions, we use just the geometric cross section. But for the ions, like because we have C2s in the disk and this ion collisions, we use Coulomb cross section that will give you much larger cross sections, and that results in much shorter mean free paths. We'll also look at the MI in the disk, and this is just the rough estimates because the magnitude of the magnetic fields in debris disks are uncertain. But we find we can have some MI turbulence operate at some scale heights in the disk. And we also have some gas observations and dust observations for clumps in one representative debris disk, beta peak. So this one's for the C1 detection and this is the last continuum. We see that at about 55 AU, there is a clump in both dust and gas. And we try to explain this by vortex, so by the Raster wave instability. And we plot the surface density variation along radius, and also this is the vorticity. But unfortunately, the Stokes number, which is the coupling between the gas and the dust, is very large because the gas surface density in the debris disk is very small. So for this large Stokes number, the dust and gas are not coupled very, very well. So even though you have a vortex, gas vortex, driven by the Raster wave instability, it's not very possible to have a dust clump.
Sorry, what's the physical side of the graph to the stigma? Because what kind of observation is that? It's a millimeter observation?
The dust continuum is millimeter.
Right, okay. So you're observing the continuum and you said you are at Stokes 1000 in the continuum.
Right.
At 50, okay.
Right. So, right, because
but then your gas is a fluid?
The gas is still a fluid.
Still a fluid?
It's not collisionless, it's still collisional.
Okay.
Mm-hmm. Yeah, because whether it's collisional or collisionless, it's just a mean free path over the scale height h, right? If you go above 1, then it's collisionless, but it's towards the very surface of the disk. If it's less than 1, then it's collisional. And we currently have some observations for the radial distribution of the gas and dust, and we find some of them are less extended compared to the dust. Some of the gas are more extended than the dust. And in the future, maybe we can do some 3D simulations to better understand the gas dynamics in debris disks. So I guess I will stop here and leave my summary here. So thanks. Yeah. Go ahead.
Yeah, so I have a question on, so what form of, so it's molecular viscosity, but is it predominantly shear of viscosity?
Yeah, it's sheer molecular viscosity.
Right. Doesn't that would suggest that all your gas disks should become eccentric?
That's possible. I think that's possible, but here we don't really consider eccentric to the Mayfair pass.
I know what I meant is say you start with essentially a circular gas disk. If you have a molecular shear viscosity that's high, then that disk will spontaneously generate become eccentric.
Yeah, I think so. I think that's correct.
Do we observe that, or do we?
I don't have too much idea about that.
I just wrote the text.
That's a question about it.
Yeah.
The data you show is from a bandmass observation. Right. The paper set has 10.
Yeah. Okay.
I know there are a couple of other observations. There's band 6. I saw preliminary results from band 6, and they also published band 7. But the contrast, interestingly, is different. So in our data, we don't see the asymmetry between the two sides.
You mean you don't see the
So you
cloud?
see the right side is brighter than left side in dust continuum. That's not the case in the band 7.
Okay. Is there a reason for this?
I don't know. So it's more like a ring to me, not a vortex.
Okay.
That's the case. And also it's change over bands. Are you planning to model multibands?
Not yet for this one. I guess for different bands, you have different wavelengths, so that makes different dust size. Is that true?
Oh, you're right. There's sensitivity to different sizes.
But I don't think that's going to be that different to influence your Stokes number. It's not like orders of magnitudes difference, right?
There is a question online. What is the average mass density in kilogram per meter cube of the disk? I'm quite ignorant about this disk.
Okay. Mass density of the disk. So let's look at this plot. So this plot showing is showing. So for the densities, I'm not sure. I think in CGS units. No, I can't remember the number. Yeah.
On the data peak case, so we know that there are at least one planet inside. So, like, is the clock you see like related to the planets of this planet, or is that nothing to do? Or...
Say it again.
So in beta peak there is a planet. There is a planet in the beta peak.
Yeah.
Okay, so my question is whether the gas clump you see is related to the presence. You think is related to the presence of the planet? Do we know this or not, or it has nothing to do? Or...
So usually, I don't think the clumps are something to, okay. So if you have a planet, then it will drive, it will cover gap. So which means the surface density will vary over radius that can cover, that can drive a vortex, right? That's like in proto-plunge disks. Once you have a planet, you cover gap, and you can also drive a vortex because of the velocity wave instability.
The planet will drive eccentricity into the debris disk, and that will cause an overdensity. It does. The back direction is weak. The back direction is strong, yes. No, it's not. The back direction is also weak. I think. Have you looked at the back direction?
Just to get rid of the eye, but still see the eye.
The Stokes number is large, so I don't think the coupling is very long.
Okay.
Yeah.
I have a question on this is back on the BSI stuff. I mean, in your voice, do you manage to get how much of the sort of turbulent cascade do you manage to get? Going to be compared against any predictions from wave turbulence there?
What you mean, like the cascade I get?
Like the power spectrum.
Yeah, I don't calculate the power spectrum, but I think for the hydrogen instability, should be like -5 or 3. That's my guess.
I think this system definitely shouldn't be -5.
Okay.
Not that I'm entirely sure it should be. Like it's been worked out for uniformly rotating. You're not sure whether it's uniformly rotating.
Right.
Not so much for sheer.
Yeah.
Also, do you know if people are doing like this size simulation with compressible code, or it has been performed so far with uncompressible codes?
Say it again. Sorry.
So, do you know if this kind of simulation have been reperformed with compressibility?
Oh, I see.
Or have they always been performed for practical reasons with incompressible codes?
Yeah. So I think this is the only simulation for the parasitic instability of the BSI. We just done incompressibility. I think this is global. So this global simulation is compressible. But for the incompressible, it's just because the local simulation it requires the incompressible survivability.
And the boundaries, what kind of boundary do you put?
It's just periodic because it's spectral code. Yeah.
So for the resolution requirement for this, do you get like in the next slide you say that you need high enough resolution, maybe the next slide. And like did you do resolution study for also for your sweeping, or how do you anticipate it's required?
So the required is it's actually from theory. It's from the analytical derivations. It's like we calculate how many. So roughly there's for the inertial waves, this wavelength is like 1/3 of the BSI wavelength from the theory, and we from the linear theory also know like the wavelength of the BSI compared to the scale height in the disk. So you need like 3 times for this one to appear than for the BSI, because the wavelength is like 3 times shorter.
And so your resolution here doesn't really
matter. I think it does matter, because if you want to resolve, you definitely need some higher resolution. I think we tried different resolution, and 6.4 is something. If you go higher, you don't see something different. So it's a robust result.
Okay.
Yep.
Yeah. If there are no more questions also online, we can thank Sam. And that's it.
Thank you.
Thank you for joining your line. Thanks for joining your line.